Okay, this is lesson 7.2, volumes of solids of revolution. Basically what we're going to do is we're going to take the areas that we did in 7.1 and we're going to revolve them around the x-axis or revolve them around the y-axis. The process of revolving is going to create two circles. You're going to have an outer circle and you're going to have an inner circle. So let me see if I can draw a quick kind of, let's say we had this picture right here. If we had this area inside of there, if we revolved it around the x-axis, it would, no, this is just me trying to draw it for you. It would rotate around and basically be kind of like a cone inside of a half of, sort of a half of a ball kind of a look. So if we were to slice this and take a piece of it out, then what we would see would be what we call a washer. The slice would look like this because there was a gap in the center part over here, and so that creates the inner hole, and then the outer part creates the outer hole as it revolves. And so we're basically going to take the area of this bigger triangle, the area of this bigger circle minus the area of this littler circle. So what we need are two different radii, and that's what we're going to be looking for in our problem. So for our example, what we have, it says to find the volume when the area between y equals the square root of x and y equals x squared is rotated around the x-axis. So I've gone ahead and drawn the picture for you. We have y equals the square root of x here, and y equals x squared here, and this is the area that we are revolving right inside there. So we have a couple things going on. First of all, we're going to need to know these intersection points. So we can either graph it on our calculator and find the intersection, or you can take the square root of x equal to x squared, and we can figure out where they intersect by squaring both sides. So if we square both sides, we would have x equals x to the fourth. If we subtract the x to the other side, we would have 0 equals x to the fourth minus x. And then if I factored out an x, I would have x minus 1. So my two solutions are going to be x equals 0 and x equals 1, and you can see that that's at 0 and that's at 1. Okay, so we're still going to do top minus bottom for our area, except for this time we're going to the x-axis. So we need to find two radii. So basically here's my process. This is what I do. I always start with the volume or the line of rotation. So since this is rotating around the x-axis, I'm going to put my first dot on the x-axis, and then I'm just going to extend out to the furthest curve. That's going to give me my big radius. Then if I start on the x-axis again, and this time just extend up to the closer curve, that's going to give me my little radius. So the red one that I have there is going to be the big radius, and it's going to be this part of the curve minus the x-axis. So that's going to be the square root of x minus 0. And when I do the little radius, I'm going to be doing this part of the curve minus the x-axis, which is going to be x squared minus 0. Okay, so I need some more space. I'm going to move over to the next page. So I had the square root of x minus 0 for big radius and x squared for my little radius, and I can go ahead and subtract the 0 and simplify it a little bit. And so now when I come up here and put this into my formula, the big radius is going to be squared, the little radius is going to be squared. We're going to be subtracting because we're subtracting the areas of the circle, and then we've got volume on the outside. We know this goes from 0 to 1. We know this goes from 0 to 1, so we just have to plug everything in. Big radius is the square root of x squared. The little radius is x squared squared. You can go ahead and simplify it, and you can put this in your calculator and get your answer. So when I simplified, this is x minus x to the fourth, which looks sort of familiar from when we found the intersections. And then we can integrate this with our calculator. So the volume is going to be 3/10 pi. And if we had units, then that would be cubed because that's volume. So that's how you work that out right there. Alright, let's try another one. This time I have a function, sine x, and the x-axis, so that's going to be the boundary for my area. We're just going from 0 to pi, and we're going to rotate about the x-axis again. So we're just looking at this first area, and we're going to rotate about the x-axis. So if I start on the x-axis and I go to my furthest distance, my outer radius is sine x. Now notice there's no gap down here. There's no hole. So if I do a little radius, it would be from the x-axis to itself, which would be 0. My little radius is 0 because there's not a gap. There's no gap between the line. So this time when I plug it in, my little r is actually just 0. And of course we're going from 0 to pi. So let's plug that in. So the big R was sine x. The little r was 0. So in my formula I would have sine x squared minus 0 squared. And I'm basically just going to drop off this 0 part. So I'm just integrating sine x squared. Remember we said from 0 to pi. 0 to pi. Remember that this pi that's on the outside is there because we're subtracting the areas of circles. And when we integrate this, we'll get our answer. So what you get is pi times pi over 2, or in your calculator it's probably going to be about 4.929. And we're going to round to 3 decimals. Okay? You could also have left this as pi squared over 2. Alright, one more example. This time we have y equals x squared plus 1, y equals 0, x equals 0, and x equals 1. These things all make up our area boundary that we're going to have. So y equals x squared plus 1 is my curve. Y equals 0 is the x-axis. X equals 0 is the y-axis. And then x equals 1 is going to be the fourth side to this. So we're going to be dealing with the area inside there. This time though we're rotating around the y-axis. So that means when I do my rotation, this area is going to rotate this way. So I'm going to be looking at right minus left instead of top minus bottom. Now notice for this one that there is, well, it looks like we're going to have maybe a bit of the radius would be maybe a bit of a problem. So let's see. Yeah, no, we got this. Okay, so what I've drawn right now is the big radius. So this is 1 minus the curve, but the curve has to be in terms of, let me back up and put that in a different color. 1 minus the curve, but this curve has to be in terms of x. So we would have y minus 1 square rooted would give us x. So it's 1 minus the square root of y minus 1. That's going to be, okay, I'm lying to you. Let's try that again. It's going to be 1 minus 0 because that's the y-axis. Now when we go back to the y-axis and we go to the shorter distance that's going to create our radius, that's where we're going to have the square root of y minus 1. And then we're going back to the y-axis, so that's going to be 0. So see, my long radius, let's do this back in black, was here. And my short radius was here, and that's kind of hard to tell because there's just a little tiny bit of space in there. So now we know that our let's see, we know that our y bottom boundary is going to be 0. Our y top boundary is going to be where this curve intersects this line. So in other words, where x is equal to 1 will give us our y value. So the bottom y value is 0. The top y value when x is 1, if you go back to this curve up here, then that's actually going to be a 2. So our capital R radius, our big radius, was 1 squared minus our little radius, which is y minus 1 square rooted and then squared. And then of course we have pi because we're talking about circles. So you can put this in the calculator or work it out and you're going to get an answer. So the integral itself is actually 2, and then with the pi your answer is going to be 2 pi. Now feel free to double check me on any of these answers because I forgot my calculator and I'm working them all out by hand. But those are your processes, and you can have practice problems in class.